Hi, and welcome. Today I'll be solving homework 2 for Transport 2 assigned by Dr. Carlos Co. And I currently have my work laid out here, and I also want to say apologize if my head cuts out again. It's still just an awkward setup. Before we get into it, I'm going to read over the problem and just maybe have an understanding of what we're looking at before we actually dive into how to solve it. So, looking at my notes, a 10 centimeter long uniform cross-section capillary initially contains pure liquid H2O and deuterium on its left 0 to 5 centimeters and right halves 5 to 10 centimeters. At 10 equals 0.1 seconds, the max molar flux was 2.78 moles per meter squared seconds. Pure deuterated water and density of water and deuterium are given in the problem as well, which is also stated here. So now that we actually know the layout of the problem, it's a capillary tube where on the left side it's pure H2O, and on the right side, the other 5 centimeters that's in the capillary, it's just pure deuterium. And so the first problem that we want to solve is, what is the overall mass flux corresponding to the max molar diffusion flux that we are given in the problem? So we know that we're going to want to solve for N, which is the measure of flow of just the mass flux of the system. And so this is given in grams per meter squared seconds. And we know that we're probably, since we're given the max molar diffusion flux in the actual problem, we're probably going to have to solve for the molar flux and then give that to the mass flux in order to solve this problem. And so also by looking at the problem, we know that the max molar diffusive flux for both of them is 2.78 moles per meter squared seconds. We can also apply this to the molar diffusive flux of H2O and deuterium. The only difference here is that H2O is positive and deuterium is negative. This is because the H2O will be moving to the right in the capillary tube because it's all on the left side of the mixture at the T equals 0. And deuterium is negative because it'll be moving to the left because it's on the right side of the capillary before it starts to mix. So this makes sense. As it starts to move, it'll move to the left, which is hence negative. As H2O moves to the right, it's going to be positive. And we also know that the overall diffusion in the system is 0. So there is no net flow because it is a closed system. There's nothing coming in, there's nothing coming out. It's a closed system just being mixed between the two compounds that we are given. So the first step in this actual equation and how to solve this problem is that we need to convert the diffusion flux to regular flux. So we use the equation here where the molar flux of component I is equal to the molar diffusive flux of I plus the concentration of I multiplied by the molar velocity of the system. And so the second part of the actual equation here, this concentration multiplied by the velocity, is what we consider the bulk contribution. This is going to end up being important because based on the problem, and we know that there is no net flow because it is a closed system, we can assume that the bulk concentration is negligible and equal to 0 because the velocity is equal to 0. And so this gives us the equation of our molar flux just literally being equal to the molar diffusive flux based on what's given up here. And so the molar diffusive flux of H2O is equal to the molar flux of H2O, which is equal to 2.78 moles per meter squared seconds. And that goes for the same as the molar diffusive flux for deuterium is equal to the molar flux of deuterium, which is equal to negative 2.78 moles per meter squared seconds. Now from here, now that we have our molar fluxes of each of the components that are in the system, we convert the molar flux to the mass flux, which it's pretty simple. We take the molar flux that we currently have up here, molar flux of I, then we multiply it by the molecular weight of component I, which equals our mass flux of the system for the component. Excuse me. So now once we have this, we'll take the molar flux that we currently have for each of the components in the system, and we multiply it by the molecular weight of each. 18 for water and 20 grams per moles for deuterium. And that ends up giving us 50.04 grams per meter squared seconds for the mass flux of H2O, and negative 55.6 grams per meter squared seconds for deuterium. So this pretty much tells us that for each mole that is moving to the right and replacing the deuterium, and each mole that's moving to the left and replacing the H2O, there's roughly 50.04 grams of water moving to the right for each mole, and negative 55.6 grams per meter squared seconds that are moving to the left for deuterium. So while one mole is being replaced by one mole, there's actually more mass that's being moved to the left side of the capillary because there's a higher molecular weight for deuterium. And so the last part of this problem is that we need to take the total max flux in summation. And so that pretty much is just summing up the mass flux of H2O and deuterium to give us the total max flux of the system. And so pretty much 50.04 minus 55.6 gives us a total mass flux of negative 5.56 grams per meter squared seconds. And that is going to be our final answer for number 1, which does make sense because the total mass distribution is shifting to the left as there's more mass moving to the left because of the deuterium moving there instead of water. Now, going on to the second part of the problem, we are tasked with finding the order of magnitude estimate for the max driving force at t equals 0.1 seconds. Before actually going in and trying to solve this problem, we really need to know what driving force is and what we need to do to solve that. And so, driving force here, written in green, is the reflection of the strength of diffusion between two compounds in a system. And so now that we know this and what driving force is, we can look at the original equation that we're given for driving force for a component I, which is the summation the summation of the mole fraction of I multiplied by the mass diffusion flux of J minus the inverse of those compounds divided by the concentration of the system multiplied by the Stefan-Maxwell component of the system, which is pretty much how effectively the two liquids will combine and mix together. That's pretty much what the Stefan-Maxwell is trying to do here and what it represents. But because this is a binary system, this is going to be very important. It makes this a lot easier in actually having to solve. We can get rid of the summation because we're really not summing anything up because we only have two compounds that we were given in the system. And so we can actually get rid of that summation and we can refer to the driving force as just flat out D instead of the component of DI. And this is also because we refer to as D because the flux is equal to opposite. We know that there's no actual flux in the system because we go back over here, there's no flow. So there's actually no sort of difference in what the driving force will be from right to left or left to right. It's just going to be equal and opposite. And so because this is also a binary system, we can also assume that the mole fraction of I is equal to 1 minus the mole fraction of J because there's only two components. Makes sense. And also we can assume that the molar diffusive flux of I is equal to the negative molar diffusive flux of J. Once again, it also makes sense because it's a binary system. The rate at which it's going to be moving to the right is going to have to be equal to the rate that's moving to the left, while the mass is not the same, but the total moles that are being distributed between the two are going to be the same, just opposite. And so now that we know this and we can substitute these into the equation that we have for D, we can eventually simplify and cancel out terms, do a lot of easy stuff to help make this a lot easier and cleaner. And we are given in the final equation that we have as the driving force is equal to the negative molar diffusive flux of I over the concentration times the Stefan-Maxwell coefficient for H2O and deuterium. And so once we have this equation, we can use this equation again, which is rewritten with the terms of deuterium and H2O. Also, we know that the molar diffusive flux for both is also going to be the same. And so we can go through and really just assess this after we find the concentration, the Stefan-Maxwell, and the Stefan-Maxwell coefficient. Sorry, it took me a second. And so we know that from our textbook and just given to us that the Stefan-Maxwell coefficient is always 10 to the negative 9th meters squared per second. And once we can use that, we can plug that in for D here, but we still need C. So the concentration is going to be the mass of the system, which is assumed to be 1,000 kilograms and 1,110 kilograms, respectively, for water and H2O for the system, or deuterium for the system, sorry. And we convert this into moles per kilograms, and then we divide it by the total volume of the system, which is 2 meters cubed. Once we do this, we can find that the concentration of the system that we have here is equal to 55,528 moles per meter squared. And once we have that, we finally have our concentration. We have all the components needed here to find the driving force that we necessarily need. And so the driving force is equal to the negative of molar diffusive flux, which is 2.78. So we'll end up having a positive 2.78 on the numerator, Once again, this is going to be, the driving force is going to be the same because the molar diffusive flux is the same for the system. So one will be positive, one will be the negative, depending on which one that you will want to look at. I'm just using the negative here so that we can get the positive answer, as that's just makes more sense to me. So we have 2.78 in the numerator. We divide that by the concentration, which is roughly about 55,500, multiplied by 10 to the negative ninth, and we will end up getting the order of magnitude to equal roughly about 50,000 moles per meters cubed. The exact answer is 50,064.83 moles per meters cubed. And that is how you solve question B. Now, using this information, we will go on to look on to some of these graphs that we were asked to solve for question 3. You should see most of them here. And so I'll go through and discuss how these work and what they apply to as we are going through density, the molar concentration, molar diffusive flux, and the mass flux of the system over time, with t equaling 0.1 seconds, t equaling 60 seconds, and t equaling infinity seconds, which will eventually become uniform. So starting with t equals 0.1 seconds, we are going to see here that the H2O on the density is going to be pretty much what it should be at 1,000 kilograms per volume. And we're going to see that pretty much stay solid here until we get to the middle of the mixing point. So this is at the middle of the capillary, where that 5 is, and we are going to know there that that is the initial mixing point at t equals 0.1 seconds. So we know that there's not a lot of mixing going on. The only mixing that's going to be occurring is here in the middle. And once you get past that, on the right side, the other 4 centimeters is going to be the density of D2O, which I will note here is a slightly higher than H2O because it has a higher density. It's 1110, while water is assumed to be 1000. So when we get to the equilibrium point here where it's starting to mix, and we'll see as it goes along that it becomes a little cleaner, and we'll see why that is. We can see here that the molar concentration is roughly also about the same, pretty much identical to the first graph. But the only difference here is that the 2 lines are almost the exact same because the concentrations are the same. And we can know this because we pretty much take these numbers that we have here, 1,000 kilograms, converting it to moles per kilogram, and we just convert it to liters by dividing by 1,000 liters, so we have moles per liter, and that gives us our concentration. And so we know then that the concentration of H2O is 55.56 moles per liter, and the concentration of D2O is 55.5 moles per liter. And that explains why that this H2O is just slightly larger here. Once again, the only mixing point is in the middle, and on the left side and the right side is going to be pure deuterium H2O. Going down to the bottom 2 graphs, we have the molar diffusion flux and the mass flux of the system. These make a little more sense and just are a little easier to understand. This is because the actual molar diffusion flux graph, you can see that for the first 4 centimeters, they're both pretty much not moving. Same with the back 4 centimeters. But you can see in the middle here that H2O goes positive and deuterium goes negative. This is because in those middle 2 centimeters, around 4 centimeters to 6 centimeters in the capillary, we know that H2O is moving to the right, which is why it's positive, and deuterium moving to the left, which is why it's negative. We can also, then we look down here to the mass flux, and we see that the only thing here is negative. And when you think about it at first, this might be a little confusing, but it makes sense because the mass flux is transferring to the left side because the deuterium has a higher molecular weight than water. So that does make sense that it's negative because there's more mass flux being moved. There's more mass being moved to the left side of the capillary rather than to the right because that's where the deuterium is going. Excuse me. And now we'll go to the middle ones where we have t equaling 60 seconds. We can see it's a little cleaner graph from the right side of where it's at. And this is because there's more mixing going on. The whole left side of the capillary is not going to be full H2O anymore, and this is not going to be full deuterium. But this is still slightly higher because deuterium still has a higher density than H2O, even though it's going to be mostly deuterium on that side because it's starting to mix. There's going to be some H2O over there, just not going to be as much to lower the density. And so we go down to the molar concentration of that at t equals 60 seconds. So the molar concentration is becoming a little more thoroughly mixed up. we see that only on the far left side is the higher H2O, and on the far right side is the higher deuterium. And as it goes through the capillary system, we have the equilibrium point at around 5, which is where it should be, which is where the mixing is taking place. And then it drops off as it gets to the inverse side, which also makes sense because it's just not full uniform mixing at this point. It's still going to have the majority of whichever side it started on. And so we'll go down here, we'll look at the molar diffusion flux, which is just an expanded form of this graph here, which also does make sense because there's more mixing, there's more movement of molecules throughout the entire capillary system and not just at the middle. And so H2O is moving more to the right on the entire side, throughout the entire capillary system, sorry. And that's why it's positive the entire time. And deuterium is moving to the left throughout the entire system the entire time, which is why it's going to be negative throughout the entire system from the 0 to 10 centimeters. And we go down to the mass flux, which is once again going to be negative, but it's going to be over throughout the entire system, the entire 10 centimeters, because there is more mixing and more uniform mixing going on at this point. So it's going to make sense, but it's just not as high because there's already been the most mixing at the middle ground. And finally, at t equals infinity seconds, where it becomes uniform throughout the entire system, we can see here that deuterium and H2O all are pretty much a straight line across. This is because it's going to be uniform. We know that's fully done mixing. So it's going to be just the densities of their system throughout it, 55.56 and 55.5 moles per liter, which is why H2O is just slightly larger. I'm sorry now. Deuterium is slightly larger because it has a higher density still. Sorry, I was getting ahead of myself and going to the concentration. So I'll just retract and re-explain that because it probably